All right, we're going to find some areas of some surfaces. So this is like a special case of a surface integral. So really, you can look at this on the next problem, I think problem 10. But what we're doing, as you'll see, we're integrating the constant function 1 over the surface. Okay, so there's a surface integral of the scalar field, which is the constant function 1. And this is equal to the integral over the parameter domain D times the magnitude of Rs cross RT ds dt, where R of st is the parameterization. Okay, so we're going to do number 1 first. So this is what we're gonna look at first. So number 1. Okay, so the first thing that we need to do is we need to figure out what the parameterization is. So let me just briefly show you what this is going to look like. Okay, so the intercepts, so the x-intercept is going to be equal to 2, the y-intercept is going to be equal to 3, and the z-intercept is 6. And so it's the part of this plane that lies in the first octant, so this little triangle part here. Okay, now if we look at this in the xy plane, okay, if this is x and this is y, we're looking at this part of the triangle here. This is 3, this is 2, okay, and this line here is y is equal to minus 3 halves x plus 3. Okay, so parameterization is going to be r of xy. Well, so we can write this as z equals 6 minus 3x minus 2y. So it's the parameterization of the graph of a function. So it's just x, y, 6 minus 3x minus 2y. And this right here is a parameter domain. This area, this triangle here, is the parameter domain. Okay, so now we'll just write the integral and fill this stuff in. So y is going to go from 0 to minus 3 halves x plus 3. X is going to go from 0 to 2. Okay, and now we're going to integrate Rs cross RT, or in this case, Rx cross RT. So Rx is equal to 1, 0, minus 3. Ry is equal to 0, 1, minus 2. And I will just let you compute this to get that to show that Rx cross Ry is equal to 3, 2, 1. And the magnitude of Rx cross Ry is equal to the square root of 14. So Rx cross Ry, the magnitude of that is equal to the square root of 14. So that's what we're integrating. We're integrating the square root of 14 dy dx, and this is just equal to 3 times the square root of 14. Okay. Because really it's just the square, so this is the square root of 14 times this integral. This is just the area of this triangle, which is 3. So 3 times the square root of 14 anyways, or you could just do this integral, whichever one you want to do. Okay, so just to recap, the surface area of a surface, you're doing the surface integral of the constant function 1, which is just equal to this right here. Okay, so it didn't go this way in the book, but now that we've seen surface integrals of scalar fields, the area of a surface is just the surface integral of the constant function 1. Okay. So let's now do another problem. All right, let's do problem number 4. Okay. All right, so the surface is z is equal to xy. So a parameterization could be r of xy equals xy x times y. But notice that we want the part that lies within the cylinder x squared plus y squared equals 1. So this indicates that the parameter domain is going to be a circle. So really we should do this in terms of polar coordinates. Okay, so this surface, by the way, is like the Pringle chip shape or saddle shape. So the parameterization, or a parameterization, is going to be r of theta r is equal to r cosine theta r sine theta, and the z coordinate is just x times y. So this is going to be r squared cosine theta sine theta. Okay, in the parameter domain, theta will go from 0 to 2 pi, and r goes from 0 to 1. Okay, now at this point I realize actually this is going to be a mess to compute cross products, so I don't want to completely redo this video. Why is this not erasing? Hold on, let me erase this and I'll Okay. So what happened is I realized that the method I thought was going to be easier is not the easier one. So let this be a lesson. Don't be afraid to change your method when it's not going to work. So now this is going to be x, y, x, y. In other words, we're not changing. I'm not going to change to polar. I'm not going to start in Cartesian or in polar coordinates. Okay, so z is equal to x, y. So anytime the surface is a graph of a function, this is the parameterization. And now the domain is just going to be this set x squared plus y squared is less than or equal to 1. Okay, so Rx is equal to 1, 0, y. Ry is equal to 0, 1, x. And the magnitude of Rx cross Ry is equal to the square root of 1 plus x squared plus y squared. Okay, so now we're just going to plug it into this integral up here. Okay, so this is going to be the integral over the parameter domain D, which is the set x squared plus y squared is less than or equal to 1, times 1 plus x squared plus y squared dA. Okay, now the parameter domain is a circle, so this is perfect timing to do polar coordinates. So theta, now we'll switch to polar coordinates. Theta will go from 0 to 2 pi. R will go from 0 to 1. This is the square root of 1 plus r squared r dr d theta. Let me do that. Okay, and then this is equal to 2/3 pi, or pi times 2/3, the way that I have it. Okay, so that's all for this problem.